All right. Now, um, got into really why you teach engineering for kids, we got into this just to point out is yes, we think aviation is interesting and exciting, and I've soloed. I'm not a pilot, but both Randy and Judy are both. They're involved with me. Are both pilots. I have, like I said, I have soloed, and I think that's great. But what we really got Randy and I to found the company is we want to work on making engineers, and we wanted to do this several years ago before STEM became all the rage. The goals of the class, pretty straightforward. Keep it engaging while maintaining academic rigor. And this won't be all death by PowerPoint, sorry, but we got to go through some of this. Teaching math and science and stressing the scientific and engineering methods so kids see the difference. I think sometimes people talk about teaching pre-engineering in middle school and high school. I don't teach pre-math, I don't teach pre-science, and I don't teach pre-engineering. You teach the math, you teach science. When you're teaching science, well, you're often using the scientific method. We're teaching the engineering method, and I think you're teaching the engineering method, you're teaching engineering. We like the aviation theme. Kids, I think it's ranked just behind dinosaurs and robots. We also had a goal that it didn't use any special equipment, so there's no joysticks needed. We found, previous years, I found that you have 20 joysticks in there, you have 20 kids, all you need is one joystick not working, so a 5% failure rate for just that class, and you spend all your time worrying about this joystick and not teaching the class. We also aren't using, for example, X-Plane 10 because that has some really heavy-duty graphics requirements. And frankly, most schools are either running old computers or they're buying the cheap netbooks that have no graphics capabilities. And finally, we're trying to keep the price on this as affordable as possible. It consists of two parts, X-Plane 9 and X-Plane 7, depending on what you have. And to student teacher worksheets. So it has those. It also has presentation materials such as presentation slides, videos, lessons, how-to videos, and webinars. And obviously you've seen this webinar too. But the lessons will actually kick off the class for people for 10 minutes. The how-tos are very short, 30 seconds. How do you take off? How do you read this instrument? How do you do certain things? All right. And you can get it two ways. The website itself, we have a members area, and then we have Dropbox if that's what you're using. Okay, X-Plane itself consists of a flight simulator and plane maker. The plane maker is important because in the national science standards, and if you're doing modern day engineering, you simulate almost everything before you build it. Now think about that Boeing, Gulfstream, Burt Rutan, everybody uses X-Plane for proof of concept ideas. So the kids are really getting to use the same stuff the pros are using. We've got 10 lessons. First 6 lessons are science theme. They cover forces and energy, as if you were in the national science standards. Final 4 lessons are an engineering theme. Students design an airplane in the final lesson. And this has been tested and worked out with. I work at a prep school, but at my sister engineering school in Charlotte is an underserved kids with a lot of underserved needs, and everybody's done well with this. If you are going to be teaching this, a couple suggestions: be a facilitator. Don't be a sage on the stage. Don't tell the kids every answer. When they ask you a question, ask them a question. Also, I think one good rule to do is those worksheets are really worked on. They've been revised more than 25 times and tested. So when they ask you a question, I always say, well, show me on the worksheet what you don't understand. I'll gladly answer your question. And a lot of times they sit and just read it. They figure it right out. All right? Be prepared. Coming to a webinar and doing those things, that's great. I would really be patient with yourself, because I think a lot of people going in and teach stuff think you have to be Joe Expert the first time through. Well, you can't be. The world's changing so fast, and the depth of knowledge is so great that I challenge most people are not experts. But in this case, what we're really trying to teach here is the engineering method, and and good critical thinking, which many people have. And finally, it's supposed to be engaging and fun for both for the kids, but also for you. So a sample lesson would be some kind of introduction that you would bring to the group, your class or your club. You'd show a little video we have. Then you would give a handout to the kids. I'd have them read the handout before you get them over to the computer, because the minute they see that computer, it sucks their brains in, I swear to God. I'm kidding there, of course, but you really do want to have them do the worksheets. And you then let them fly. Let them, every lab in this, they're going to be using the simulator. If you're spending most of your time lecturing, you're not doing it properly. But that's true about any of the engineering, whether it be robotics or bridges, flight, 3D printers, whatever. All right, here's the curriculum guide. You see the first 5 up through stability, first 6, I should say, and the last 4 are very much on the engineering side. First flight, just a reminder, we always start at the quick flight setup. You go to LAWI, you open an aircraft, and the plane you want to pick is the Cessna 172. Set the time for 8 o'clock. You have you hit that at the clear, so you don't have precipitation, storms, and turbulence. It's hard enough for them to learn how to fly in the beginning with that. When you go to take off, you pause it, you hit the brakes, and you pull the throttle. Okay? So later, in a moment later, it's paused. Brake lights are off. You're in full throttle. You're ready to go. In this first lab, like we talked about, it's science standards. So in that lab, you're looking at airspeed, attitude, and altimeter. And then what you do is you're having the kids fly, and then they point the nose down, and they start to see what the trade-off between airspeed and altitude, which is really a trade-off between kinetic and potential energy. And so that's really what that whole lesson's about. Now, in lesson 2, we get into forces. So we get to teach them what weight is again. We talk about magnitude and forces, all right? And then just the lab is you increase the payload, and you see what that does to takeoff distances. So they really get to do now when we set it up, by now the kids see, oh, I click on this, 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 and go through it. They will go through it really fast. They pick it up pretty quickly. So here we're changing the payload. It's at 298 right here. Let me just show you so you see it. It's 298 right there. All right. We change that pen color here. Let me go ahead. So it's 298. You change 298, change it to 600, change it to 900. Just needs to be close, so you're looking for a trend. Then we make sure and we go into data sets. We make sure we're measuring speed, distance traveled, and landing gear forces. Remember, if the plane is sitting down on the ground's got to be pushing back up through those landing gear and the same amount of load. So if you get off the ground, the wheels aren't pushing on anything. There's nothing pushing back, so the load on them is 0. Up here, the graphical is so we can actually graph it, and cockpit displays so they can take a snapshot in the cockpit. So like here's some of the graphing we do. And you can remove, see back here, there's a lot of lines here. You don't need necessarily all that stuff. Well, you can just uncheck them and suddenly you have fewer lines. Right here is where the airplane is beginning to take off. These are the landing gear vertical forces. They've gone to nothing. Here's the distance traveled. Here's the true airspeed. And so they write off the true airspeed. They take the average takeoff distance at 300 pounds, 600 pounds, 900 pounds. Then they graph that. So they're really doing the scientific method here. They're doing the whole process. Anytime we can sneak that in, I think that's a good thing. And we get kids that can explain why it is dangerous to be low and slow on an aircraft, which is pretty exciting. Okay? Do you have any, before we go on to lesson 3 and new stuff, do you have any questions? Just type them down there if you think you got a question. Or raise your hand. All right. If that's the case, we're going to do lift. This is lesson 3. And you're looking at, now if we did gravity and weight, lift would be the opposite force. We talk about that in both angle of attack, angle of incidence, that lift is really a function of both not only airspeed, which most people realize, but it's also that angle of attack. And we build angle and attack and the angle of incidence in the wing. There's always a little bit of angle of attack in the wing, or as you flew, the plane would always have to be pulled back just a little bit with, not a lot, but a few degrees. By putting that angle of incidence into the wing, we don't have that. As a matter of the class itself, we do both Bernoulli's principle, Newton's third law as an explanation of lift. It's all low pressure in the top surface, higher pressure in the bottom. Now, what's that caused by? For years I grew up, it was always just explained as Bernoulli's principle. People had some issues with that idea and have argued it's more Newton's law. We give both explanations. Now, the way we teach the lift lab, by the way, is by stalling the airplane. If you look at this airplane right here, you see these lift vectors. These green lift vectors right here. And what's great is on the tail, the vectors are going in the opposite direction. If we define this as positive, then the tail is going negative. And we'll get back to that when we talk about stability and airplane acting like a teeter-totter. But if you look up here, you see the green is the vertical lift. Yellow is basically the horizontal lift. And then red, you don't really even see that much of it. There's some drag due to induced drag. And what we have the kids do is a powered flight. They go to take off. They start climbing. They keep it full throttle, but they pull the nose up. They keep climbing. They keep climbing. The airspeed's bleeding off. The airspeed's bleeding off. They see one wing gets less left than the other wing. It falls out of the sky. And then the lab is, well, as it's going down, your airspeed's gaining, but you're really not getting that much lift. And then the minute they're both going down fast, and then they add a little bit of angle of attack, these lift vectors take off. It's kind of you can measure lift as well on the settings, and it's a neat competition to see who can get the greatest amount of lift. Now we are ignoring the amount of G's being pulled on the pilot and on the airplane, and totally out of spec, and you would never do that in the real world. But that's the great thing about a simulator. What's also great about that, by the way, is I was at a major air show this summer, and I had a lot of flight instructors explain to me that they have their students still don't quite get that. That lift is both an angle of attack and airspeed. And not a stall, really understanding a stall. So I think it's an important thing for everybody to know. Okay. Let me see if I get any more questions. If not, I'm just going to go ahead and proceed on here. Drag is the next force we're working on, and it's going in the opposite direction than thrust is going. Forces drag goes along the same direction as thrust, but it's going in the opposite way. And in this lesson too, the kids, to kind of mix things up, we have them fly a different airplane, a King Air, twin King Air. They want to fly they want to fly combat aircraft and everything else. I really suggest for your teaching that so you don't let them do that in the beginning. Save that kind of stuff towards the end. We talk about drag, talking about both induced and parasitic drag. Induced drag being created by the lifting surface itself. When you get more lift, you get more drag, as you probably know. And parasitic drag is drag of the shape of the body, and just sticking your hand out the window kind of drag. And we talk about that in terms of looking at flaps and how flaps both slow you down but allow you more lift at a slower speed. And so we tie in that to talk about drag because you see a significant difference there. Planes are so clean today, it's hard to do things to change the drag, but we use that. Plus, gets us ready for lesson 5, which is stability. And excuse me, which is landing the aircraft. If the first two lessons are each at least 1 day, the second lesson could be day and a half. Third lesson's half day to a half period to a period. So flaps and then landing. Landing tends to be much shorter. So if you get, your first lesson, time you teach it, and the first lesson runs over, don't worry, we can make it up in the fourth and fifth lesson. Doesn't show what I want there, so I popped off what I want. But we also have lesson 5 here. I'll pull it up in a second. In lesson 5, they go ahead and they're going to land going down a runway. And we just have the guys control that when you do go into 5. Let me go ahead and pull that up. Bear with me a second. Right. And pull this up. All right. Take a look at this. Lesson 5 is on thrust. Okay. And head over here. I wanted to pull that as the background, but it might not let me do that. So we'll go back here. So lesson 5 is about thrust. It's all about you land by controlling that amount of thrust. So we have the kids come in. We have them explain where the PAPI is, Precision Approach Path Indicator. It's red and white lights you see at the end of the runway. All red, you're too low. Half red, half white, you're right. All white, over flight. Okay, and what we really work on is don't over control the airplane. Just keep the throttle, the plane's descending. Then to spruce things up, we actually leave, the one time we leave the airport, we don't do this at Lawi, we go over to San Diego International, go into situation, under files, you can go under situation, and you can do an aircraft carrier approach. And then if you want to make that interesting, you may at rough at seas, and you can even try doing it at night. And man, you get a lot of respect for our pilots that are doing these night operations, night carrier operations. That is not for the faint of heart. So I would just say on lesson 5, control the throttle at 1500. Don't go left and right and worry about things. Just let the plane fly and land itself. The kids tend to overcorrect. The kids tend to crash a lot in the beginning. If you've not done this before, you will crash a lot in the beginning. That's totally okay. Another thing you can do with the kids for fun, if you've got a little extra time and they've been all psyched about doing this stuff, is I have like little landing air races. I have everybody start at final approach at 3 nautical miles out. That's a setting you can come in at, and we see who can land the quickest. So that's kind of a trade-off between trying to come in as fast as you can, but not overshooting the runway and not crashing the airplane. Okay, do we have any questions about that? All right, now I'm going to go back to this. I want to get into lesson 6 here. Under flight controls. But before we do that, this is usually the time we break it up and we start making the airplane. We make a little airplane. And this way the kids get to modify and change a plane using what they know. This is one of those Jetstreams, Balsa Wood Jetstreams. They've been around since we were kids. I guess I remember going to my grandparents, they gave me a quarter and I could buy one. I think these are now $2, so you can still get them. You just put them all together with balsa wood. The kids, it looks like this. Kids learn to work with balsa wood and they break sometimes. It's not a big deal. But everything is pretty much push it together. You go out there and fly, get like a few second flight usually. Kids get all excited. But then you ask them, well, as a good engineer, what can we do to make this plane fly better? And what the kids do is they usually tell me get rid of the cockpit You can see in the shot. We no longer have landing gear. I have some kids, that red cap that holds the prop on, they'll cut half that cap off and put a little glue on it. So they'll do all that to the airplane. We'll also, because of this, we're going to also replace that motor. I'm going to show you. I'm going to go forward and then come back. You're going to have a much bigger motor on there. So they talk about the 4 forces. What are the things we can increase and decrease? Can't do a whole lot about lift, but we can do something about thrust. We can do something about drag, and we can do something about weight. The other thing we can then introduce to the kids, the idea of keeping the airplane stable. That if it's got all this power and speed, if it's not stable, it might have been okay at slow speeds, but the faster you get going, the more power you put to it, that instability becomes a bigger and bigger problem. So what we do is take the wing out, we score it with a pencil, glue it up like you can see on the left side right here. See it right there. We snapped it up. The important part is, I usually say it's like 1.5 inches here. That's not important to me, is that this wingtip up is at the same angle as this wingtip over here. Make sure they're symmetrical. That's the important thing. All right? Then you've got this plane ready to go. If you can afford a winder, you get a winder, because these big motors, you can go a lot longer. And if you do it right, it goes from 1 to 3 seconds. The other flights, these are 6 to 10 seconds. And the kids really get pumped because you just showed them, oh, so all the things we're talking about really do apply. And then you start to get into some trade-offs. That's also neat. That's one of the important things about engineering. Okay, so that's a good way to, now if you got younger kids, 5th and 6th graders, you go up to this point and then you say, okay, let's stop here. And then with 7th grader, and you can actually talk a little bit about stability with them. All right, and I'm going to bring this up for you to see. Let's see an actual lesson. Pull that up. All right. Whoops. It's not the lesson I want. Pull this up. All right, great. So what this does is we talk about the different controls on the airplane. We talk about roll along this long axis. You roll the airplane. Oops, sorry. Pitch is up and down here with the nose, and yaw is left and right. So you take the kids out on the runway, and you let them go out and just make sure they understand those controls. They've been flying and landing it, but it was a surprise to me that they didn't understand which part of the movable surface of the airplane was causing that. So we do that. Then we ask them, well, basically we talk a little bit about stability, and we talk about the tail and the roll of the tail in the airplane. And we do that by talking about a feather. And what we want to do there is we want to say, well, if you didn't have a feather, the tail feathers on an arrow, what begins to happen? And what they learn and what you learned in high school classes, pretty soon, you shoot the arrow out of the bow. If it didn't have feathers, it's going every which way. And it may even hit the tree stick first, and not even hit the arrowhead. So the tail on an airplane acts much like the feather, dampens out any kind of forces that want to take the airplane off of its path. And then we had dihedral that helps with some, helps to keep the plane wings level. So we talk about that. But here's the thing now that we can start doing some more simple machines and some other science. We talk about pitch stability, up and down. And we get into the idea of where the center of gravity is, where the center of lift is, and the different moment arms, the tail moment arm and the center of gravity moment arm. Now this can get fairly sophisticated, so it depends on your kids. I have taught this and have had pretty good luck with 7th graders, teaching them torque and the whole 9 yards, but yours may not. So we just show them that. We ask them some questions. We talk about balance and safe flying. crocodile got loose on an airplane, caused the airplane to crash because everybody ran to the front by the cabin. Climbing higher, you want to go into more detail, we can actually start looking at the torque or moment. We start using frogs and toads and kind of comparing them. Why can a frog that was half as much as the toad there be in balance? Well, because he's twice the distance from the fulcrum. And in an airplane, the fulcrum is the center of lift, which is usually about the third of the way back on the wing. The big frog in this case is the center of gravity. That's where all the weight, if you could balance the airplane with your finger, and you could only do it one point, that would be the center of gravity. So I have a distance from that center of gravity to the center of lift. So that's the center of gravity moment arm. You have a center of, but to balance it, if the center of gravity is a little ahead of the wing, then you got to balance it from the other side. And that's where the tail moment arm comes on. And that's why, for example, in that 172 you saw, there's lift vectors on the wing going up. If we define that as positive, the lift vectors on the tail are going down. Okay? Now, so, for example, tail moment equals tail moment arm and lift generated by the tail. That's this here. Center of gravity moment equals the tail moment when the nose is not pitching up or down, but in equilibrium. So if that center of gravity moment arm equals the tail moment arm, well, the plane's not going up or down anything. It's staying stable. If the plane's pitching up, you ask it, is it the center of gravity moment or is it tail moment? And you can talk about the tail moment, which is, by the way, caused by the movable surfaces on the back of the tail. If the plane is pitching down, which is greater, COG moment or the tail moment? Well, COG moment is, as well as the tail's moment surfaces. But if you weren't rolling the surfaces, if, say, we kept the plane, we weren't going to change the controls, and all we're trying to do is figure out, the only thing you change is the center of gravity moment or the tail moment. If the plane's pitching down, then that would tell you the center of gravity moment is larger. We do something where we look at the elevator deflection and we see, well, how much elevator do you have to add when the plane is out of balance, basically. You see that 17.3, those are inches. And that's 17.3 inches from the center of gravity. And then 22 inches, so the negative and the positive, it's all relative, related back and forth on it. What we really just want you to see is the impact that balance plays in the airplane. So one direction, if you think of the center of gravity, if one side is, all you can do on this thing is move the center of gravity in one direction. I'll show you in a little bit. It either goes negative or it goes positive, and that negative and positive are just defined as being negative and positive. There's no real reason to be that other than to demonstrate one's going in the opposite side of the center of gravity from the other one. And I'll show you here in a moment. In fact, let's do that right now. Bear with me, I want you to see this. We used to fly X-Plane during the webinars, but the internet can't keep up with the X-Plane that way. So I tend to just show it from menu choices and things so you can see it better. Okay, it's because I don't have it on my computer right now. It doesn't show the disk. No big deal. Now, what I'm talking about here is when we load the aircraft, weight and fuel, right? So there's a center of gravity when you balance. You can either pull it all the way this way, inches from the default 22 inches back towards the pilot, or negative 17.3 in the opposite direction. And that really, we look at that center of gravity and have the kids fly the plane and see how much up or down elevator they have to add to try to hold, maintain flight. And you see pretty quickly you can get that out of balance, and then you got problems because you can't. There have been plenty of accidents where the pilots didn't take the time to make sure their center of gravity, that the weight was all balanced with the weight and balance tables, and then when they took off, the plane either nose went straight up or they went straight down, and they couldn't do anything about it. Also, let me show you under above, you can do you can have the AI take off on your aircraft. So if you have one child that's struggling a little bit with the takeoffs, you know, you don't have anything to worry about there. Just go to the AI and let the AI take off. All right. Now let's go back here. All right, let me go back over. So if we, so that way you see the balance take off. Now let me do this. Whoops, didn't mean to do that. Let me pop this up here. There it is. So get that average, and you again ask them, well, which one has the larger tail moment arm and how much force is being produced? And so we get that kind of questions. Okay? And you start to see that the roll of that long distance by, you know, this distance increases, gives you a lot more larger force. And so, but some ways also makes the plane that it gets longer, then the pitch stability becomes a little more of an issue then, because that becomes very powerful on the end of the tail. And then remember, the thing with X-Plane is, and using PlaneMaker, you draw the plane like that, it's going to fly like that, both good and bad. So that's one thing that's important to understand. All right. Let me ask you, Fred, you got any questions? Fred, you got any questions, man?
Well, no, not so far. Can you hear me?
Yeah, I can hear you great. Now your sound is good, golden. Okay. Well, kind of gone because there's just us. We've kind of gone through what my first and foremost deal I wanted to get done tonight, and that was through lessons 3, 4, 5, and 6. What I would say on lessons 7, 8, and 9 is you get an engineering method. It gets a lot into trade-offs, and we get into the iteration process. So that way, the kids see, well, wow, I can change my aspect ratio. They use math. They figure out what the aspect ratio is. They know what's in design spec. If it's outside, they can't use it because it either means the airplane won't take off or a customer won't pay for it. And they find that using a calculator or doing it in their head, that saves them from building it and trying the airplane out. So we're trying to use math in a relative way. They also find out, like, for example, well, increased aspect ratio means a shorter takeoff distance. Well, this is great. Well, then why doesn't every airplane have huge aspect ratios? So they start to begin to see, you know, really engineering is a series of compromises